Good afternoon, everybody. So we've hit 1:30, so we'll get started. I just want to welcome you to our whiteboard session. My name is Leah Miller. I am the marketing manager here at RGL. So for today's event, we're going to be exploring how advanced nozzle technology is changing the completions game. Today's open discussion is going to be presented by our flow control engineering manager, Dr. Dazu. And before we begin, I just have a few housekeeping notes to go over. We have noticed that the video quality of the presentation can be affected when audience members have their feeds turned on. I know a lot of you just have sound, so that's okay, but keep your video feed off until we open the discussion at the end, and of course, mute your microphones as well throughout the talk. Now, to give you some background at RGL, some of our best ideas stem from whiteboard sessions, and we wanted to find a way to carry that over to the industry in a knowledge sharing format. So we started hosting these whiteboard sessions beginning earlier this year on various topics, hosted by our subject matter experts, and they've been a great success so far. So just to let you know, today's talk should run about 20 minutes. Afterward, we want to hand it over to the audience to ask questions and have an open conversation about how this technology is impacting our industry. If something comes up that you want to ask throughout the talk, you can type it into the chat message window if you like, and we can open it up for questions, and you can ask using your microphone or your camera, or just we can read it off the chat window as well if that's easiest. And we hope you'll participate because we're eager to hear your viewpoints on today's topic. So to begin, I'd like to formally introduce Dr. Dazu. Da brings to the energy industry a broad range of experience in flow control device, thermal completions design, and multi-phase flow dynamics, wellbore modeling, as well as reservoir simulation. His PhD and postdoc research in fluid mechanics from the University of Chicago and MIT have been integral in designing RGL's Nozzle series, as well as NALU, which is our multi-phase flow dynamic software used for near wellbore regions. His unique patented technologies and extensive experience in computational multi-phase flow dynamics helps clients all over the world find success in their production efforts. So he's a great resource. I hope you guys enjoyed today, and I'll let Dodd take it from here.
Good afternoon, everyone. Thank you, Leah, for the very nice introduction. And so I'm here to share my slides. Can you see my slide?
Yep, you're good, Da.
Okay. Yeah. I feel very pleased to present our nozzle technology and share some fundamentals of our DF and DS nozzle today with the industry. We have RGO. We have many flow control nozzles for different applications. But today, due to the limited time, we will focus on the two nozzles, DF and DS nozzles, and I will explain what they are and how they are functioning. This is the outline of today's presentation. First, we will give a very brief introduction on RGL's nozzles, and then we will introduce the mechanism, the function of the DF nozzle, which is a nozzle to choke back steam, and then we will talk about the DS nozzle, which is a nozzle for supersonic gas or steam injection, and in the end, we will give some conclusions. So this slide shows the RGL's D nozzle series. So as you can see, we have 6 nozzles patented and available for the industry. We have DF nozzle, which is for steam choking, DS nozzle for steam injection, supersonic steam injection, and DM nozzle, that's a multi-directional dual directional nozzle for steam supersonic steam injection and for steam choking in the other direction. And we have an NCG blocking nozzle, the DB nozzle, a water choking nozzle without moving part called the DR nozzle. And recently we have patented and designed and patented a DJ nozzle. It's for solvent operation. So today, as I said, we will focus on the first and second nozzle, the DF and DS nozzles. Okay, so DF nozzle is an inflow control nozzle for steam choking, and its design philosophy is that our goal by using DF nozzle here is to increase the emulsion production rate and to reduce the steam production rate as much as we can. To achieve this goal, we want to utilize the flashing mechanism and we want to get the unwanted fluids fully flashed or get flashed as much as we can. And the equation here shows that it's a mass flow rate equation, and it's derived from the definition of the mass flow rate and the modified Bernoulli equation. So we can see that M is a mass flow rate, and CD is a discharge coefficient, and A is the open to flow area of the nozzle. Rho is a mixture density, and delta P is the pressure drop across the nozzle. So we can see that when the density of the fluid is reduced, its corresponding mass flow rate is reduced as well. So that's how the DF nozzle is working. And the flashing itself is a combined manifestation of thermodynamics and hydrodynamics. So we will go through the flashing mechanism in detail in the following slides. From thermodynamics point of view, flashing or cavitation is very similar to boiling, and they are both about the liquid getting into the multiphase liquid and vapor regime. And the difference is that as for flashing, it is a process under constant temperature, and while boiling refers to the process at constant pressure. But besides that, there is further fundamental difference, and we'll show that later. Flashing itself is a nucleation process, and the nucleation is not the causation of flashing. It is like a catalyst of flashing. So we can see from this PV phase diagram, when a liquid when its pressure lowers to the saturation point, it will have two choices. Either, excuse me. So if there are sufficient nucleation sites available, then the flashing will happen right away, and the pressure will follow this horizontal black line before it goes to the multiphase unstable regime. But if there is no nucleation sites available, the pressure will go deeper and deeper until it hits the spinodal curve or homogeneous nucleation limit before it gets into the unstable multiphase liquid and vapor regime. So the other interesting fact about and this dashed curve is called the van der Waals curve. And the interesting fact is that the area enclosed by the dashed curve and the horizontal black line is equal to each other. That is because the integral of the Gibbs free energy along this line is equal to 0. And the reason that we study nucleation, or we take care of nucleation, is that nucleation can enhance flashing, or it can promote flashing. So that's why we need to take it into consideration when we design a nozzle and when we select the surface roughness of the nozzle and also the material of the nozzle. This slide shows the CFD simulation of some of our nozzle designs during the process. This blue dashed line, V2, V15, N2, V15, is our best performing nozzle. And we can see that its pressure dives very deep, and the time this nozzle spends on flashing is the longest compared to the other nozzle designs. And as I said, this nozzle is the best performing nozzle in terms of steam choking. So when we design the nozzle for steam choking, the extent that the pressure dives and the length, the pressure stays at flashing is very important. So this this video shows the flow loop test that we performed in a third-party lab, and the upstream condition is a saturation condition. Which means that any pressure drop downstream will trigger flashing. So, and what we are showing here is the outlet condition. We can see that the multi-phase flow are coming out from the outlet of the nozzle, and that is the wet steam is very intermittent and very unstable. This is meeting our expectation. So the other thing is we need to evaluate the nozzle performance, and there used to be two groups of thoughts in terms of the nozzle evaluation for steam choking effects, and one group of people saying that, hey, well, our goal is to produce as much as liquid as possible. So the liquid discharge coefficient, the liquid flow rate is what we want to improve. And the other group of people say, no. Actually, the biggest enemy of thermal operation is steam choking. So we want to choke back as much steam as possible. So what we are doing here is to combine these two thoughts together, and this is actually a balancing act. So we developed this measure. It's called the steam choking ratio. It is defined as the mass flow rate of the cold liquid versus the actual mass flow rate. So we can see that if there is no steam, this ratio will be equal to 1. But if there is flashing, so that the actual mass flow rate will be reduced, so this ratio will be higher, will be greater than 1. And on the y-axis, it shows this ratio. So we know that the higher the number on the y-axis, the better the steam choking effect will be. And on the x-axis, we define a normalized temperature, or sometimes we call it a subcore index. So the lower the value on the x-axis, the lower the subcore is. And when the value on x-axis is equal to 0, that means we are at saturation condition. So we tested a few nozzles, a few of our nozzles, and also the orifice. So we can see that the orifice can choke back 23% of the steam, and our DF nozzle can choke back 72% of the steam at saturation condition. Okay, so but besides that, we want to have a second look at flashing. So what is flashing really? So flashing is a process involving bubble growth and collapse from microscopic description. And the Rayleigh Plesset equation, as I'm showing here, is the governing equation for that process. Due to the limited time, I'm not going go through and explain, derive this equation. But if you are interested, we can discuss offline. As I said, flashing is very similar to boiling, but there is fundamental difference between these two processes. Flashing is inertially controlled, which is controlled by the term in the red circle, so that the bubble radius will grow with time, while the boiling is thermally controlled by the term in the blue circle, so that its radius, the radius of the bubble in boiling, will grow with square root of time. So we can see that after some time, the size of the bubble in flashing is way bigger than that of the boiling, and that is particularly the reason why flashing is so violent than boiling, and the flashing can damage. Actually, if we do some back of envelope calculation, we'll find that even with the diffusion effects or some other viscous effects, the temperature and pressure in a collapsing bubble during flashing can still be 5,000 degrees Celsius and 10 to the 5 psi. This is really amazing numbers. But fortunately, this collapsing process will only happen in microseconds. So usually we don't, if it just happened for a short period of time, we don't have to too much worried about that. But when we design the nozzle and when we select the nozzle material, the flashing and its consequent damage should be considered when we do that. Okay, so that was the DF nozzle, and now we are talking about the DS nozzle. It is a nozzle. It is an outflow control nozzle for supersonic steam or gas injection, and if we want to inject steam or gas at supersonic speed, we want to get the pressure recovery ratio as much as we can, so that we will not lose a lot of total pressure along the way. So in comparison, we can see that the conventional nozzle or port when we use conventional nozzle or port, if we want to reach Mach 1 at the throat, the downstream pressure will have to be less than 0.56 or 56% of the upstream inlet pressure. And that means 44% of the total pressure will be lost on the way. And that 44% of the total pressure you can do useful work to recover more oil, and there is a lot of cost associated. But if we use the DS nozzle, we can see that its pressure recovery ratio is 93%, and we will only lose 7% of the total pressure. So 44% compared to 7%, the efficiency improvement and cost saving is right there. Here we are showing a simulation case study for a customer, and they approached us and want us to design a CFD injector well, and they want us to compare the DS nozzle performance and the port performance with and without packers. So the length of the well is 950 meters long, in horizontal, and we can see that the steam quality of the DS nozzle at the toe is about 14 to 15% higher than that of the port well. So that is because when you use DS nozzle to inject steam at supersonic speed, since its pressure recovery efficiency is much higher, which means that you do not need very high upstream pressure to inject steam at supersonic speed. And a lower upstream pressure means lower saturation temperature, and then the heat loss from the tubing or casing to the reservoir will be reduced correspondingly. So that is why the DS nozzle can save a lot of energy. And the DS nozzle will particularly be useful for when you drill a long horizontal wells, say like 1,500 or 1,800 meter long horizontal wells. That it will keep the heat all the way to the toe. Okay, so again, so here we are taking a second look at the supersonic gas or steam injection, and the key to design a supersonic nozzle is to reduce the increase of entropy. Like there are many ways to achieve that, but you have to find a way to reduce the increase of entropy as much as you can. Then the efficiency can be improved. And the other point is that supersonic multi-phase flow will be much different than the supersonic ideal gas or single phase or ideal gas or single phase dry steam. That and I'm going to show it here. So what we are seeing here are the velocity and the temperature of a supersonic gas with very small solid particles after the shock wave. And what I'm showing here is the simplest case. There is no phase exchange. There is no interaction between particles, and just small particles in the gas. And we can see that the figure on the left hand side shows that if the velocity relaxation time is smaller than the temperature relaxation time, we can see that the particle velocity and gas velocity will converge to each other much more quickly than the convergence of their temperatures, and this actually matches our expectation. And if the velocity relaxation time is higher, is longer than the temperature relaxation time, we can see that the velocity will between particle and the gas will converge much more slowly compared to the temperature. So and again, this is just one level above the ideal case, and we are still working on some multi-phase case with heat transfer and with particle interactions. Okay, so here are the conclusions. As we can see that steam-related problems are very interesting because they are multi-phase. They can be multi-phase. They are non-equilibrium state, and but on the other side, these complications or these interesting things are making the steam-related FCD design very difficult, very challenging in terms of nozzle design and in terms of flow loop testing and operations. So the success of FCD requires extensive knowledge and also the joint industry collaboration between the vendors and the operators. So the entire industry need to work together to tackle this problem and to better the operations. And today I'm just showing you some of our understanding And on this on the flow control device and the thermal related nozzles, as you can see, there is still a lot of room for further development and optimization of the flow control devices. So I think the entire industry need to work together and get it better. Thank you very much.
Thank you, Da, for that great insight. That was fascinating. And I hope that now our audience, we could open it up for some questions. If there's any questions you want to ask directly to Da, just you can either type them in the chat window or you can open up your microphone and go ahead and ask. Okay, well, I have a couple questions for you, Da. I wanted to get your take on where do you see the future of flow control technologies heading in terms of how it relates to choking all the various unwanted fluids. Do you have a bit of an outlook on what you think we can expect?
That's a good question. I think first of all, the reliability is very important for the operators. So they want to make sure the other operator they want to make sure that the tools or the devices that they are installing in downhole will work or will not fail. There will not be any disaster associated. So because especially for some very high stake projects, I think reliability is number one, and that is why we are leaning toward designing the nozzles without moving parts due to its strengths, its easy operation, and a lot of risks can be mitigated by using the nozzles without moving parts. I think that's what we are doing. And the other thing is there is no single solution for all the problems that we are faced today by using FCDs. So FCD is not something can magically solve the problems. I think sometimes we need to customize the device for certain operations, and but I think most importantly, the the vendors and the operators should talk to each other and to solve the problems together.
Okay, that's great insight.
Hi, Darwin. Alberto here speaking. One question. So Leah asked you about the future of FCD, but I wonder, or I would like to get your opinion about the current state of the industry or of the FCD industry in Canada, and if you consider that the current state right now is successful in terms of handling certain breakthrough issues, which is the most common problem in Canada for FCD completions, right?
Yeah. I hope that I can answer this question, Alberto. So I think when I came on board with RGO 5 years or 5.5 or 6 years ago, at that time, the industry was trying some FCD technologies, but there were still a lot of doubts, and one major question people have had back then was how can we produce so much oil from this very tiny hole, and how can we make sure that it will give us what we really want or what we really design. And so because the open to flow area of that tiny hole is so small compared to the regular slotted liner or screens, right? So people had concerns, but after a few after the trial projects and after this 4 or 5 years, people have got confidence and people have seen success in terms of using flow control devices in the field. And I think before that, like 3-4 years ago, the tubing deployed FCDs were more commonly used compared to liner deployed. But now the industry is more leaning toward using liner deployed FCDs coupled with sand screens when they drill new wells or sidetrack wells to because of the performance in history and also the cost saving. So I think that is the trend I can see. But as for future, I would say there are some other issues we need to look into, such as solvent, such as non-condensable gas together with steam, and sometimes we will see bottom water. So how to solve these problems properly, and that should be the new challenges for us.
This is Majid Saidi from Strathcona Resources. Thank you for your talk. I have a presentation. I have a question on your slide number 12.
Okay. Yeah.
So you mentioned about the heat loss in this that is less in your DS
Yes.
nozzle, if I'm not mistaken. Couple of questions here. Was that designed on a liner system or it was a tubing deployed system?
It is a tubing system.
Okay, tubing system. So what I didn't get is if we assume the steam chamber temperature is more or less, or pressure is more or less constant, which means the P out is constant.
Yeah.
Does it really matter what the P in and for that matter the saturation temperature of the inside of the liner is? Does that even change anything on the heat loss at all?
Yes, we did see that because you P out is fixed, but P in if you want to reach supersonic speed, with the DS nozzle and with port, their P ins will be different, and the P in for the DS nozzle will be lower compared to the P in for the with the port. So that is why.
No, agreed. But
Yeah.
what in that case, what do we mean by heat loss? Heat loss to me means the heat that is going away from the steam chamber, not the heat that eventually enters the steam chamber.
Oh, okay. I think what we are calculating, or we are paying attention to here is the heat loss, is heat exchange or heat loss between the tubing and the reservoir.
Yeah. Okay. Got it. So again, from the SAGD operations perspective, yes, there will be a heat transfer, more heat transfer, like from the heel or the toe of the red case versus black, but really that heat eventually goes to steam chamber, right?
Yeah. That's true. That's true.
Yeah. Okay. So that's one question. The other one I was going to ask is, so in this situation, do you keep the end of the tubing closed, or do you leave it open?
Yeah. Close.
Any mechanisms as to make sure there is no steam condensate basically staying at the end of the tubing there?
That's a good question. That is good question. I think that is why we are doing the multi-phase one, a multi-phase simulation. It's and with condensate and with particles. At this moment, we are just using the homogenized model, and that is and what we are trying to do is to make sure through the tool design, we want to make sure that the steam condensate at the bottom of the tubing or the pipe will be picked up and fully mixed with the live steam before it goes out to the annulus or to the reservoir. So that is more on the tool design side, but we are thinking of doing that. of that.
Okay.
Yeah,
that's great.
Yeah.
Thank you. And then last quick one: are these supposed to be shiftable ports or shiftable nozzles or not? Like they're all just open all the time?
Well, it's we can do shiftable and non-shiftable, but usually the customer, it really depends on customer. But usually, as for the steam injection, customer wants to have a shiftability in their tools. Yeah.
I see. Thank you.
Yeah. Thank you.
Great questions. Okay, we have a question from David. He wants to know, what do supersonic flows at the end of the nozzle mean for erosion?
That's a very good question. So we want the supersonic. So that is associated with the nozzle design, the actual nozzle geometry and the nozzle design. So if and that is why why our nozzle, our DS nozzle has a pressure recovery chamber. So the function of that pressure recovery chamber is to recover pressure, and also we want the shock wave to stand inside of the nozzle, so that the velocity of the steam will be significantly decelerated, and there, so which means that what you will have at the exit point of the DS nozzle will not be supersonic, it will be subsonic, and yeah. So there will be very minimal concern on erosion. Actually, the speed of the gas or the steam at the outlet will only be about 40 meter per second. Yeah.
Okay, great. Thank you. Do we have any more questions before we wrap up today? If not, there's a lot of opportunities for us to get in touch and obviously talk more about this fascinating topic. But we are over our time today and we don't want to take up too much of your day. So we'll wrap up. And I just want to thank everyone for watching today. If you find this interesting, we're going to be saving this as an on-demand viewing video. It'll be on our YouTube channel, and we'll share it, of course, on our LinkedIn page. And you can rewatch it, share it, ask more questions, happy to help. So stay tuned on our social media channels for upcoming whiteboard sessions. If you want to learn more, of course, visit our website at rglinc.com. And again, thank you. Thanks, everyone.
Thank you.
If you don't mind, I will stay for a while and ask you another quick question.
Oh, sure.
Should I ask or should I wait?
No, yeah, you can ask.
Yeah, go ahead.
Yeah, just for your DS nozzle on the slide that you are slide 11, what sort of delta P across the nozzle are you envisioning? Is it like 100 kPa, 200 kPa? What sort of deep?
Less than I can tell you that it's less than. It depends. Actually, this still it really doesn't matter. It's just a ratio, and so if the case that we tested was less than 100 kPa.
Okay, so with 100 kPa you can achieve
Yes,
essentially
that's true.
choking.
That's true.
Okay.
Yeah,
Okay.
that's true.
Thanks again. It was really good.
Always. Thank you.
Okay.
Thank you for
Have a good one.
Yeah.
Bye-bye.
Bye-bye.
Excellent. Okay, I think that wraps up. I don't see any more questions in our chat, Daw. So again, thanks for everyone for joining us, and stay tuned for future whiteboard sessions. Thank you again, Daw, as well.
Okay, thank you, Leah. Thank you, everyone. Bye-bye.
Thanks, Doc.
Thank you. Cheers. Bye-bye.